Good evening, everyone. Good evening. Confirm me, how are you all? And are you all getting my voice and video properly? Just a second. All right. Okay. Thank you, Ankit. Okay. So, in today's topic, we are going to start organic chemistry, and the topic for today's class is going to be inductive effect. So, we are going to see the concepts of the inductive effect. What is this effect actually means? Okay. So let's start the topic for today. So as I already mentioned that today's topic is going to be inductive effect. Organic chemistry, when you start preparing for these kind of examinations, GPAT or NIPER, this is the subject that really makes your rank. The subjects like 𝘂𝙎𝙎𝙎𝙄𝙊 and other pharma related subjects are especially designed for the qualifying this kind of examinations, but for the rank, for a good rank you have to go through the topic of organic chemistry. It's a scoring subject, but most of the students really skip this subject by having like, no, we can't going to study the chemistry portion, but chemistry actually decide the rank of the students who are preparing for this kind of examination. So I should prefer all of you and advise you like, yes, you have to go through the subjects of chemistry. And so today let's get started with our simple topic, but the one of the most important topic, and with all the concepts of organic chemistry, this like inductive effect or all any of the electronic effects are really helpful in understanding the concept behind the electrons. Organic chemistry is all about electron chemistry. You can simply write it down like this is all about electrons chemistry. If you really want to study about the organic chemistry, you have to go through the concept of electron distributions. Sir, hello sir, I have a question in GC Prime course. In one day, how many lectures are there? Ankit, initially there are 2 lectures, but after the passing of time, there could be 3 or 4 lectures in the morning as well as in the evenings. So it will be depending on the cases, like which time is suitable for you, that will be preferred there. Okay, so as I mentioned, like electrons, the chemistry is all about like organic chemistry. In modern organic chemistry, basically the electrons are preferred. How these electrons distributions are there in a molecule, in a compound, since Organic chemistry is made up of covalent bonds. The carbon hydrogen, the carbon hydrogen bonds like hydrocarbons and their derivatives. After skipping one of the hydrogens, substituting hydrogen, one of the other elements, it could be there, and that is the derivatives of hydrocarbons, and a new compound is basically seen there. Like when we talk about the methane, let's start with the very simple like structure, that is of methane. CH4. This is methane structure. In this methane structure, you can simply see like carbon is bonded with 4 hydrogen atoms, and before starting the inductive effect, you have a brief knowledge about the electronegativity. So with this simple structure, we first will be focusing on the electronegativity, and later on we will be having inductive effect related with that particular concept. In this structure, we can see like carbon is bonded with 4 hydrogen atoms, and we know very well like carbon have tetravalency. Carbon can bond with the 4 atoms. Carbon can form 4 bonds. Here carbon hydrogen share one electrons in each bond. Like carbon, let's suppose this is electron of carbon in this bond, and the hydrogen also shares 1 electron during formation of this bond. Again, let's suppose this is the electron of carbon, and here we are having hydrogen's electron. Same as well in all the 4 cases. In all these cases, we can see like since there is a covalent bond formation between carbon hydrogen bonds, and this covalent bond formation leads to the transfer of, or you can say the sharing of electron between both the participating atoms that are actually making a bond between them. Like here in the cases, carbon is making bond with the hydrogen atom. So hydrogen atom and carbon are actually sharing one electrons each for the formation of this bond. So this is all about a covalent bond. So they are covalent bonds. They are covalent bond where both the atoms, carbon and hydrogen, are actually sharing one electrons for the bond formation. Now, the tendency of each participating atoms of a covalent bond to attract electrons. Here we can see like these 2 electrons are actually present between both the carbon and hydrogen orbitals. Now the tendency of one of the atoms to attract these shared electrons toward itself, this is all about the electronegativity. And this is going to be more towards the atom that are actually just close to the noble gases. Like we can see fluorine, chlorine, bromine and iodine, just 4 atoms. And next we are having fluorine, oxygen and nitrogen. These actually atoms are more electronegative. And why so? These fluorine, chlorine, bromine and iodine are actually just 1 electron short for attaining the noble gas configurations. And thus these atoms, when they are bonded with in a covalent bond with any of the atoms, they actually try to attract those electrons toward themselves so that they can attain the noble gas configuration. And that's why we say like fluorine, chlorine, bromine and iodine are having higher electronegativities. So electronegativity is none other than attraction for electron in a shared bond between 2 atoms. And oxygen as well. Oxygen, due to very smaller atomic size, this atom also have higher tendency in a covalent bond to attract the electrons toward itself. Like here we are having carbon, hydrogen. In organic chemistry, we say carbon and hydrogen are very good friends. Carbon and hydrogen. Why? Carbon and hydrogens have nearly same electronegativity. Nearly nearly same electronegativity. Same electronegativity. It means if the electronegativity of both the atoms are same, the tendency to attract the electron, shared electron pairs toward itself is, you can say, neutral. It means like these electrons, the shared electrons, are actually present just in the center of a covalent bond between the carbon and hydrogen atoms. So there is no any generation of charges. Why charges? So why we are talking about the charges? Inductive effect actually leads to the polarization. And this is only, this inductive is none other than, if you understand electronegativity very well, inductive will be just the same like the electronegativity. The whole phenomena of inductive effect is based only and only on the single concept, that is electronegativity differences. Here carbon, hydrogen, all of the bonds are having same electronegativities, and the electrons are actually present just in the middle of the bond, in the center of the bond. So there is no any electron uneven distributions. It means all of the bonds are having neutral, they are non-polar, they do not have any poles formation. And when we are talking about the poles, it means that whenever there is a difference in the electron density, if one of the atom is getting more electron than the other, this leads to the polarization, this leads to the formation of poles. And here we are having all the carbon hydrogen bonds with the same electronegativity. Good evening, Rajiv. So they are actually present just in the center of the bond. So there is no any polarization that can be seen in these kind of bonds. But if we, let's suppose, if we substitute one of the carbon hydrogen bond, let's suppose we are having this, and okay, 1 1 1 and this one. Now here we are having chlorine and we are having hydrogens and hydrogens. Now this is carbon hydrogen electron, carbon hydrogen electron, carbon hydrogen electron. These electrons are present just in the center of the bonds. We know that electronegativity of chlorine is very much higher than the carbon. So the electron of carbon that has to be present at the center of the carbon chlorine bond, this is like let's suppose this is the chlorine's electron. This is what has to be electron distribution that has to be present for a non-polar case. But what happens here, whenever there is a substitution of the carbon hydrogen with any of the other element, any of the other atom, it may lead to the polarization, it may lead to the polarity between the bond. Why? Since the chlorine is more electronegative than carbon, what chlorine is going to show here is it is going to attracting these electrons toward itself more, and the tendency for the chlorine to attract these electrons, these shared electron towards itself, leads to the electron deficiency at the carbon. And why? More electronegative chlorine is going to attract these carbon's electron toward itself. It is not permanent displacement, it's not like it's not going to be permanent movement towards the chlorine, but whenever the carbon is bonded with the chlorine after substituting hydrogen, it always, and you can say this kind of electron distribution is seen, like the electron of carbon is more shifted, more displaced towards the chlorine. Carbon's electron is more and more influenced by the chlorine, and leading to the uneven distribution of the electron between the carbon and chlorine bond. And this leads to the polarity. And why polarity? Look, actually the electron of the carbon is a little bit more far from the carbon. This leads to the dilemma in the carbon, like, oh my god, my electron is actually going far. It means that each of the atom is actually having the same number of electrons and protons. If the electron are slightly more far from an atom, it means that the charge of proton is going to be higher. It means that carbon is actually going to have a positive charge, partial positive charge, while the chlorine is getting one of the electron towards itself. It means electron are actually having negative charges. So chlorine is actually getting more and more negative charge. So there is a partial formation of a negative charge towards the chlorine atom. Partial negative charge. And when this kind of phenomena actually happens, whenever this kind of phenomena happens, there is always and always a polarity inside a bond. This is a non-polar. Why? There is no any uneven electronic distributions, but whenever there is a shifting of hydrogen and addition of chlorine seen, the hydrogen is substituted with the chlorine. This leads to the polarity. This was non-polar molecule, the hydrocarbon, while this structure is actually having a polarity. There is actually formation of poles. There is actually formation of charges. They are partial positive charges, but still they are actually having the charges. It leads to the polarity in that particular molecule. And thus, inductive actually came into existence. Like whenever there is electronegativity differences between the molecules that are actually between the atoms that are actually forming a bond, this leads always to the polarity. And this polarity actually decides the chemical natures. These kind of phenomena are actually helpful in this describing what this kind of molecules are actually going to see the chemical reactions and why the chemical reactions of those particular types are taking place in this kind of compounds. Like, just for a single a reminder for you, the carbon in this case is basically going to have more reactivity towards an atom that are actually having a higher electron density. Why? Since this carbon is actually having electron deficiency. The carbon electron deficiency, this carbon is actually shifted its electron towards the chlorine. A partial displacement of the electrons towards the chlorine. It leads to the electron deficiency towards the carbon, and thus if any of the atoms that are actually having a higher electron density in form of like lone pairs or any negative charges, these kind of reagents will be more and more reactive towards this electron deficient carbon center. And this electron deficient carbon center is more reactive towards the atom that are actually having higher electron densities. Like if we are having, let's suppose an atom and a reagent that is actually having electron deficiency. Let's suppose there is an atom, there is any reagent that are actually having electron deficiency, positive charge. These kind of atoms, these kind of reagents can never attract to the side that are actually having electron deficiency. As you all know, same charges repels each other. And in this case, this electron deficient atom can never attract, can never react with this carbon that is actually having partial positive charge. Like we have seen nucleophilic substitution reactions, nucleophilic addition reactions, electrophilic reactions, how actually their mechanism and why only electrophilic reactions are taking place in those particular type of compounds. Like in a simple, there is a single reaction of the aromatic compounds. All the aromatic compounds, in simple we can see like all the benzene rings. the reactions of benzene are actually more and more for the electrophilic kind of reagents. Benzene shows very and very fewer number of reactions that are actually nucleophilic, that are actually a nucleophile, that is an electron rich center are very much less reactive for the benzene. The reason behind this is like benzene is already acting as an electron rich center, and when an electron higher density center reacts with the benzene, that is not possible for the benzene to be reacted with that particular kind of reagents. Same here, like alkyl halides, we have seen alkyl halides actually shows nucleophilic substitution kind of reactions. Why? Nucleophilic substitution, it means like a nucleophile is approaching towards the compound and it reacts with that particular compound, leaving one of the nucleophile from that particular compound and adding itself with that particular compound. A nucleophile substitutes another nucleophile. It is only and only due to, like, yes, the compound is having electron deficiency. If a nucleophile, that is an electron rich center, is approaching towards that particular electron deficient center, it may lead to the reactivity with those particular species and leading to the removal of this bond. The electronic effects that we see here, inductive, it could be inductive effect, resonance effect, mesomeric, that is also known as hyperconjugation, electromeric. These four phenomena, these four electronic effects are actually helpful in predicting what kind of reactions a compound is going to show with a particular set of reagents. Like we have seen this inductive effect concept from the very beginning, like in the schooling as well as in the when we're in the second or third semesters, and again, and each and every year, like we are talking about the GPAT or NIPER examinations or any of the pharma competitive examinations, the questions from these kind of topics are always there in each and every examination, and still we are not able to solve those kind of reactions, those kind of questions. Why? We just have seen the phenomena, we have never ever studied the concept, we just have studied the phenomena. What actually these phenomena are telling to you, what actually the applications part of these particular phenomena are, you have never gone through all of them. So in simple, if you are preparing for these kind of examinations, you have to go with the application portions. I know you have seen this inductive effect phenomena many times, but still you are not able to solve the questions. Why? You haven't gone with the application part. You have just read the concept, okay, that's enough. But that actually isn't the demand for these kind of examinations. So you have to go with the application portions as well. Look, again we are having another example. Let's suppose we have carbon, hydrogen, hydrogen and hydrogen and hydrogen, and this is a non-polar compound. There is no any polarity, there is no any electron uneven distribution, there is no any electron deficient and rich center. And when we are talking about the electron deficient or electron rich center, it means like we are actually talking about the distribution of the electrons, distribution of the shared electron towards both the atoms that are actually making a bond. Now again, if we are having like, yes, carbon, hydrogen, 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 and we are having a chlorine bond here. So we just have seen like, yes, this is going to be partial negative, this is going to be partial positive, and that's all. What about the longer chain lengths? Let's suppose we are having another carbon chain that actually looks like something this, CH3, C, CH2, and let's suppose we are having fluorine. So this fluorine is actually getting partial negative since it's bonded with the carbon. There is a electronegativity difference between the fluorine and the carbon. So this carbon is actually getting partial positive charge. Okay. Now this carbon is getting partial positive, that is this carbon is actually electron deficient. This carbon is actually getting electron deficiency. And the carbon, since this carbon's electron deficiency, this is having electron deficiency, this family member of the carbon is going to help this carbon. Why? This CH3 group going to donate its shared electron more towards the carbon. Why? Let's have an example like we know there is also a carbon-carbon bond, and carbon-carbon, since both the carbons are having same electronegativity. If the carbon is getting electron deficiency, this carbon is having electron deficiency, tendency to attract electrons for this carbon has increased so many folds. When there is deficiency, there is always a hope like, yes, now I have to bring something. This carbon is having electron deficiency. Now the tendency for this carbon to attract electrons has increased so many folds. Now this carbon is going to attract the shared electron between this carbon-carbon bond. The bond between this carbon to this carbon, there must be only possible due to sharing of electrons. One electron from this carbon and one electron from this carbon is shared between both the carbons for formation of that particular covalent bond. Since this carbon is having electron deficiency, since fluorine has displaced the electron between the carbon-fluorine bond, now this carbon displaces the electron of this carbon-carbon bond toward itself, creating a partial, very low, but yes, there is also a very low partial electron deficiency in this carbon as well. So actually, if there was a hydrogen only, look, if we are having CH3 and CH2 hydrogen, I am writing down like this, it is also CH3. There is no any electron distribution unevenly. There is no any polarity. This is an ethane molecule that is actually having non-polarity. Both the carbons are having same kind of electrons. There is no any uneven distribution of electrons that is seen. But whenever we removed this hydrogen and added a fluorine atom, we can see there is a electron distribution completely changes. Complete change in the electron distribution. And we can see the fluorine leads to the electron deficient carbon centers, while this fluorine is actually having electron richness. So when there is a inductive effect phenomena takes place, it's a permanent phenomena. Why permanent, and what do you mean by permanent phenomena? Inductive is actually a permanent phenomena. Permanent means whenever there is fluorine or any electronegative atom that is actually having more electron density, more electronegativity than the carbon is bonded with that particular carbon atom, there will be an electron deficiency and an electron rich center. Till the time this fluorine is bonded with this carbon, there will be this kind of electron distribution. But if we remove this fluorine and add the hydrogen again, it will be a zero. There will be no any polarity that can be seen like here. So inductive means whenever there is a electronegative difference electronegativity difference in atoms are bonded, there will be a partial distribution, partial displacement of electrons in that particular molecule. Till the time that particular atoms are in bond with each other in a covalent bond formation, there will be that particular polarity. It's seen throughout the time. That's why we say, like, yes, inductive effect is a permanent phenomena. It is not going to be null and void till this fluorine is present here. But if this fluorine is removed, it will be again same. Like there will be no any electron difference in the molecule. So that's why this inductive effect phenomena is a permanent effect. It's a permanent effect. Now again, this fluorine is actually can be seen like, since this fluorine is attracting the electrons, and all those atoms that are actually having higher electronegativity, higher tendency to attract the electrons in that particular covalent bonded atoms, to attract the electron towards themselves, they are known as -I effect or electron withdrawing groups. Like this fluorine can be called as, like, this will be a -I group, and all those groups that are actually having tendency to attract the covalent bond, to attract the electrons in a covalent bonded molecule toward themselves, they are known as -I groups or -I effect. This fluorine is actually showing a -I effect, -I phenomena, minus inductive effect. That is known as these fluorine, these all those atoms that are actually attracting the electrons in a covalent bond will be known as electron withdrawing groups. Electron withdrawing groups. Electron withdrawing groups, and also known as -I effect. This kind of effect will be known as -I effect, since inductive effect is also known as I effect. I effect in short, inductive I effect. Inductive I effect. Yes, Somnath, you can contact Ankita ma'am or any of the teachers, faculty members for this kind of informations. Okay, all right. Now the atom or groups that are actually having tendency to donate electrons, like here this CH3 is actually displacing its electron towards this CH2 group. So this kind of groups will be known as +I effect, +I group, +I group, +I group, or electron donating groups. Electron donating groups. Electron donating groups. Yes, Somnath, as I already told you, like you can contact Varsha ma'am, Ankita ma'am, or any of the other members that whose number is present to it in your mobile phone. So you can contact any of them for this kind of information, regarding this kind of information. So this is all about +I and -I. But how we are going to decide which group is having electron donating tendency or which group is actually having electron withdrawing tendency? That is the point. So there must be a reference. There must be a reference bond, reference covalent bond. So what is that particular reference? We have took the example of CH3, that is carbon hydrogen bond. So if the tendency of any atom to attract the electron toward itself is more than a carbon hydrogen bond, this carbon and hydrogen bond This is taken as a reference. Like if the tendency of any atom to attract electron is more than a carbon hydrogen bond, that will be a minus I group, minus I effect, or electron withdrawing groups. And if the tendency of any atom is more for the electron donation than the carbon hydrogen bond, that will be known as plus I effect or plus I phenomena. Plus I effect or plus I phenomena. So yes, this is about plus I effect and minus I effect. Now let's take some examples. How this plus I and minus I effect are actually going to influence the application parts. So I have an application, first application, like carbocations. What are carbocations? When there is a cationic charge present on the carbon atom, that is known as a carbocation. Like we are having CH3, CH3 and CH3, CH3, and this is carbon having positive charge. One of the bond of the carbon is broken in such a way like the carbon is getting positive charge. So this is a carbocation and we are having another case, hydrogen, hydrogen and hydrogen. There is also another carbocation. So in both these cases, if I ask you, what do you think? Which carbocation is actually more stable? Look, these carbocations are actually more reactive. They are actually reactive intermediates. They are formed only during a reaction, during a chemical reaction. And they are short-lived fragments. They are more reactive and they react with any of the nucleophiles, any of the center that is actually having higher electron densities, and thus making a product. But if we compare the reactivities, what do you think? Which carbocation will be more stable and which will be more reactive? The reactivity is inverse of stability. If any compound is more reactive, it means like it will be less stable. Okay. So now what do you think? Which will be more stable? Which carbocation is more stable? How to decide the stability of carbocations, carbanions, acidic strength? They are actually applications that are derived from the inductive effect. And now, which carbocation is more stable? We can see like here carbon, hydrogen, carbon, hydrogen and carbon, hydrogens are present. This carbon is actually having electron deficiency. Electron deficiency, and here this carbon is having electron deficiency. Since the carbon is actually having deficiency, since the carbon is actually having positive charge, it means that the carbon is having same kind of electron deficiency. The magnitude is same for both the carbons. But what these substituents that are actually bonded with that particular carbocation are going to affect, are going to be influencing with that particular carbocation stability. Like here we are having just carbon hydrogens, 3 carbon hydrogen bonds. So 3 carbon hydrogen bonds are present here, and we know very well like in a carbon hydrogen bond that are actually reference, there is no any transfer of electron between both the atoms in that particular covalent bond is seen. So there will be the same amount of positive charge. There will be no any increase or decrease in positive charge that can be seen. But here in this case we are having a methyl group, that is carbon that is having positive charge is bonded with the carbon that are actually having hydrogens. So this alkyl group, this will be acting as a plus I group. It means the electron between this carbon-carbon bond are shifting toward more this carbon positive, since the electronegativity of this carbon is increased. Why? Since it is getting positive charge, it is having electron deficiency, so it will be having more and more reactivity, more and more like it will be having effect for grabbing the electrons toward itself. So this will be going to shift partial electrons towards this carbocation. This will be also showing same phenomena. This is also showing same phenomena. The electron deficiencies now are having different magnitudes. Why? There is no any phenomena in this molecule that is present in this. Why? These three methyl groups are actually shifting a sigma electron, shifting the electrons of that particular sigma bonds towards this carbocation, towards this electron deficient carbocation. This is leading to the decrease in the electron deficiency. For a hypothesis, you can see, like, let's suppose we are having 100 electron deficiency. Just a hypothesis. Let's have 100 electron deficiency that is seen in this carbon, and 100 charge electron deficiency is seen on this carbon. Okay. Now, deficiency is same, but the influence of the attached, the substituents, what they are going to see, so there is no any transfer of electron from these substituents towards this 100 electron deficiency carbon. But in this case, let's suppose if all these three groups are shifting 10 electrons, 10 electrons towards this carbocation, this is going to have 100 minus 30, that is just 70 electron deficiency. Just a hypothetical case. Now, just 70 electron deficiency is seen on this carbocation due to the presence of these plus I groups that are actually transferring, that are actually displacing its electron towards the more electronegative this carbocation, more electron deficient carbocation, and leading to the more and more stability. Since this is having 100 electron deficiency, this is having 70 electron deficiency, and the reactivity will be like both of them are actually having electron deficiencies. So they are going to have reactivity, like they are going to attract towards negative charges or any of the reagent that are actually having electron richness. This is having 100 electron deficiency, this is having 70 electron deficiency. The tendency to attract with that particular electron rich center for this is more. It means this is more reactive than comparing with this carbocation. It means like whenever there is a carbocation, the plus I groups always leads to the stability of that particular carbocation. In simple, you can write down like stability of carbocations. Stability of carbocations. Stability of carbocation is directly proportional to plus I groups. More the plus I groups are present, more electron donating groups present, more and more will be the stability for that particular carbocation. So this first and second, we will be having first is more stable than the second. This is our answer. This is our answer. Stability of first carbocation is more than the second one. Now, again we are having another here, let's suppose carbon and let's have again CH3, hydrogen and hydrogen, carbocation and chlorine. There are two cations, one of them and the second one. What do you think, which will be more stable? Which carbocation is more stable among both of them? What do you think, according to you, what do you think, which cation, which carbocation is more stable? Now these are the application parts. Which carbocation is more stable? We know very well, like carbon is getting positive charge, it means that that carbon is having electron deficiency. They can be only stabilized when there is actually transfer of electron towards them, that particular carbocation, that leads to the electron richness towards that particular carbocation. And whenever there is electron donating groups attached with that particular carbocation, they are actually increasing the stability. They are actually stabilizing that particular carbocation. Now, in the first case, we are having carbon, hydrogen, carbon, hydrogen. They are having null and void, zero electron densities transference between both the bonds. But the carbon and methyl bond, this bond is actually having this CH3 will be going to show like this is a plus I group. That is, this group is going to show electron donating nature. So this CH3 group will be donating electrons towards that particular carbocation, that leads to the decrease in electron density. Like again, for an hypothesis, let's suppose we are having 100 electron density deficiency. So this methyl is actually displacing its electron towards that particular electron deficient carbon and making that electron deficiency reduced to that 90, let's suppose. But in this case, we are having no effect with the carbon hydrogen bonds, but this chlorine, we know very well this chlorine is actually having electron attracting nature. That chlorine is actually having more and more electron negativity than the carbon. It means that carbon is actually having electron deficiency. This carbon is already electron deficient, and this chlorine is making more electron deficiency towards this carbon. So let's suppose we are having 100 electron deficiency here. This chlorine is actually making it more electron deficient, and now this carbon is actually having electron deficiency of minus 115 electron deficiency, let's suppose, or 110, any of the hypotheses that you can simply assume of. So this electron, that is minus I group, this chlorine is actually having minus I nature. This chlorine group is actually producing a minus I effect, and due to its electron withdrawing nature, electron attracting nature, this chlorine is leading more electron deficiency towards that particular carbocation. It means, like, whenever there is a stability of carbocations is compared, we always go for the groups that are actually bonded, are showing plus I phenomena, plus I effect, electron donating natures. The electron donating nature groups always stabilizes the carbocations, while if there is any group or atom that is present with that particular carbocation bonds that leads to electron deficiency, they always destabilizes that particular carbocation. So stability of carbocation is directly proportional to plus I group, but inversely proportional to minus I groups. If there is any minus I group is bonded directly with that particular carbocation, this will be leading to electron deficiency, more electron deficiency over that particular carbocation, and thus destabilizing that particular carbocation's stability. Got it? Just confirm me. This is the one of the application for the inductive effect. This is application part. The first application part, stability of carbocation. Stability of carbocation. Okay. If you have any of the doubts regarding this, you can raise your comment here. No comments? Okay. Stability of carbocations. So you can write down these phenomena, these relations. Okay. So this is all about today's class. We will be discussing the other applications like stability of carbon ions and the most important, acidic strength. How to decide the acidity of particular compounds. We will be discussing all those applications in the later classes. I hope you like the class, you enjoyed the class, and you grab the concept behind this inductive effect. All right. So thank you so much everyone for joining with us, connecting with us. We will be meeting again with some other concept in some other classes. Thank you all.